Okay, we're going to talk a little bit about angular velocity, and not really so much a deep dive into the concept of angular velocity, but more as a means to kind of understand it as part of our overall learning objective, which is to understand more about trigonometric functions. In order to understand angular velocity, we first have to understand velocity. Velocity, most commonly, usually you see it as velocity is equal to a distance divided by a time. In different classes, like in physics or in calculus, you'll see different symbols, but for the most part, it's the rate of change of something. Like how far does it go in a given amount in a unit per unit time. And we are going to be talking about circles. So here's a circle. And if I had a thing on this circle and it was going around the circle, well, the distance, right? This distance here, for example, from there to there, that's some distance s, right? If we had a center, this is the center of the circle, and it forms this angle theta here. That arc length is s. And so as it pertains to like circular motion, the velocity, or what we call like an instantaneous velocity at some point in a circle, you can imagine that we have a velocity going off some direction, right? The direction of the velocity is tangential to the circle, but we would have a that distance s, right? Now it's no longer d. We would just call that distance s. Right? It's still divided by some unit time. Now we also know that s, the arc length, is equal to r theta. That is the arc length of a circle, where theta is in radians. Okay, that theta is in radians. All right, that's pretty important. So that gives us this equation that velocity is equal to r theta divided by t when we are talking about velocity, or the linear velocity of some object rotating in a circular pattern. Okay, so angular velocity, it's a very similar idea, except for now, when we have a, like if this was our distance that we traveled in a certain amount of time. Now what we're interested in is how much did the angle change in that set amount of time. So it's a rotational velocity. It's an angular velocity. And it would make sense then that would equal, let me use a different color, that would equal the amount of change in theta per unit time. Okay, and we have a different letter, not v, to represent angular velocity. The letter is omega. It's a Greek letter, and it's omega, and it looks a lot like a W with the ends curled up. Okay, so uh, now angular velocity and linear velocity are very closely related. Okay, let me rewrite what we had for linear velocity. It was v is equal to r theta divided by time. And so what you can see is, right, if we take, this is theta over t, and this here is theta over t, so why don't I just substitute omega in for this theta over t? So the relationship between angular velocity, omega, and linear velocity, v is equal to r times omega. Now, of course, if I was interested in finding omega and I was given linear velocity, I would just rearrange this equation and say that omega is equal to r, sorry, how come I can't figure this out right now? Sorry, v divided by r. Um, v divided by r. Okay, so this doesn't seem significant, but it's actually very powerful math. It's a very powerful relationship. It lets us calculate things like how fast something, when we talk about satellites and stuff, like how can we know what their velocity is in space if all they're doing is just orbiting? And it's really a fascinating relationship. So let's look at a couple quick examples here of what that looks like. Here's a cool problem that we can solve using that relationship we came up with. If you tie a ball to a 3 meter long string and spin it around your head at 1 revolution per second, how fast is the ball moving? So something we should point out here is 1 revolution per second. That is talking about an omega. That is an angular velocity. It's some amount of rotation per some unit time. And we see the most common way that we see angular velocity represented, like in the real world, is as RPM. Like if you've ever driven a car and you see the tachometer, that's the RPM like gauge, and that says a revolution per minute. And then 3 meters, obviously this is going to be talking about a radius. So if we were standing here, I'm going to try to draw a guy or a person, and they're twirling a thing around their head, right? And the radius of that thing is so there's a ball, right? There's a ball at the end, and the radius is 3 meters. How fast is that ball moving? That's what this question is asking. Well, we know that V equals R times omega. Okay, so what this really comes down to is unit conversion. And we can just figure this out. Velocity is equal to the radius, which is 3 meters, okay, times the omega, which is, let me write that, that is 1, okay, revolution per second. Now, that units right there tells me it's 3 meters revolutions per second, which doesn't make any sense. And so really what we have to do here is just convert revolutions into a more useful like unit of distance that we're like that makes sense to us. And then maybe if seconds, if what we end up with is fine, then that's fine. But we might also want to convert seconds to a unit of time that's more like standardized to the point where we have some sense of how fast this actually is. So let's do this. We would need to multiply this by a conversion factor to get rid of revolution. So in one revolution, how far or how many, maybe how many radians are there in one revolution? There are 2 pi radians in one revolution. Radians. So I know I wrote radians there, but technically radians is actually a unitless measurement. And so what we end up with here is 6 pi radians, right, per, 6 pi radians meters, right, per second. And radians, really, this isn't factor in anything. We've already multiplied by the radius here. So if we multiply a radius by a radian, we just look at the units of the radius, which is meters. So we have 6 pi meters per second. Now 6 pi meters per second is like 18 something-ish. So it's like approximately 18-ish meters per second. Now, if you know how fast 18 meters per second is, that's great. But for me, and I'm in America here, I don't quite have a good way to quantify that. Now, I know that 3 meters is about 10 feet also. So if you're not familiar with how far 3 meters is, it's 10 feet. So this is a fairly long string that the ball's connected to. So let's try to get this 18-ish meters per second into a more useful or a more kind of common unit of velocity here. So we're going to take that 6 pi, and we had meters per second. I want to put this in miles per hour. So I'll multiply this by, there are 1,000, about 1,609 meters in 1 mile. Okay, and we can also say that there are 60 seconds in 1 minute and 60 minutes in 1 hour. And what that's going to let us do is it's going to cancel the meters, and there's meters here, seconds and seconds, the minutes and the minutes. So we'll be left with miles per hour after we do this math. And what we end up with is a miles per hour of about 42.17 miles per hour. So that's pretty fast. If you walked outside your house and there was a car driving by you at 42.17 miles per hour, you would be like, yo, slow down, that's too fast. And so 42.17 miles per hour is pretty fast. That's a pretty interesting thing. And you could tell that if we had a larger radius, like if we increase the radius of this thing to be like 20 meters, which would be, I'm sorry, not 20 meters, 20 feet, so closer to 6 meters, this would be even faster, be twice as fast, which would be like 85 miles per hour, which is crazy. One more example here. If a car is traveling 50 miles per hour and the wheels on the car have a diameter of 20 inches, how fast are the wheels turning? Okay, here's a car. Probably have pre-drawn the car or something. Boom, super cool car. And if it's going 50 miles per hour, that means that every point on the wheel is also going 50 miles per hour. It's actually going kind of 50 miles per hour, but it's going 50 miles per hour also. And so what we're looking at really is a circle where the linear velocity, the tangential velocity is 50, miles per hour. Okay, and we want to know how fast, if it's obviously it's rotating, right? How fast is that rotating? Okay, so well, we can set that up. We know that B equals R omega, but this time we're looking for omega, so it would be V divided by R. And so the velocity is 50, and we're in miles per hour. Okay, and the radius is, so we're going to divide this by, there is one uh, one radius, right? One radius is, or one radian actually, is 10 inches. Okay, so we can do this here. Now we'd be in units of miles uh, or we'd be in units of miles per like hour inches, which doesn't make sense. And so what we're going to do is convert our miles into inches so that when we have, it'll give us a better, the units will jive a little better. So let's multiply this by our unit conversion to get into inches from miles. So there are 5,280 feet in 1 mile. Okay, and then there is in one foot there are 12 inches. 12 inches. Okay. Then we also know, so now we would be in units. Let's look what the units would be. We have miles and miles cancel. We'd have feet and feet cancel. So now our inches and inches would cancel. We'd have some number of radians per hour. Which, okay, that's a little bit better, but I don't want to know radians. Maybe I want, because radians per minute doesn't make a lot of sense. What makes more sense is revolutions, right? We want to know like what are the RPMs maybe of the wheel, right? So how many radians are there per revolution? Well, there are in one revolution, right? There are 2 pi radians, right? One full revolution or 2 pi radians. So now I would be in units of revolutions per hour, but I probably want to have it in minutes. So instead of hours, there are 60 minutes in 1 hour. Right now the hours units will cancel out. The hours units will cancel, and we'll have a unit. After we do all this multiplication, we will have inches, or sorry, we'll have revolutions, right? We forgot to cancel out these inches. We'd have revolutions per minute. Okay, so this ends up being, 840.34 RPM, that's pretty fast. Now, also, if you're not sure what an RPM is, like when you're driving your car and you look at the tachometer and you see it's some amount of speed, this should tell you that RPM is the thing you see on your instrument panel is not how fast the wheels are turning. Okay, because if you can imagine, if I was instead I had 3,000 RPM, which is a fairly common reading to see on your instrument panel, you'd be going more than 3 times faster than 50 miles per hour. So you'd be going like 170 miles per hour. That's obviously not the case, because you could have 3,000 RPMs on your tachometer while you're going like 5 miles per hour as you're like accelerating from a stop. So RPM, just so you're aware, is how fast certain pieces inside of your engine are turning. They are called the camshaft and the crankshaft. They control how fast, how many times per second or how many times per minute the pistons basically go up and down. The pistons, but the valve covers and the pistons, not the valve covers, but the valves go in and out, and they control the different cycles of your internal combustion engine. So it just has to do with the power output. So how is this, like we talked all about this thing omega, right? We talked all about omega, angular velocity. Why is this relevant at all to trigonometric functions? Here's why it's relevant. So here's written here is a standard trig function, and notice that there is a letter or a symbol that we can use in a trig function, and it's a W here in Desmos, because Desmos won't let me use an omega. But this is omega, and as I change omega, I have this strange like compression of my trig function. If you notice these 2 black dots, okay, if omega was just 1, meaning essentially it's a standard, they're this far apart. They are 2 pi apart. That's actually something called the period. And as I then adjust that, you can see that those two black dots, they kind of get pushed closer and closer together as I get values larger than 1. Or if I were to get values smaller than 1, they get farther and farther apart. And so that omega is directly related in some way to what's known as the period of a trigonometric function. And trigonometric functions, they're periodic, and another word that we sometimes use for that is circular. And so how is this really related? What is the relationship? Why does angular velocity have anything to do with the period of a sinusoidal or trigonometric or periodic or circular function? Well, there's a reason for that too. As I spin this bike tire fairly slowly and walk to my left, you can see that the tennis ball traces this path, and that is a sinusoidal path. Now I'm going to do it again, but I'm going to spin the bike tire significantly faster, and you can see that the tennis ball is going to trace a similarly sinusoidal path, but it's much more compressed now. That's because as omega increases, we have a decreased period. And that relationship is simply t, the period of a sine function, is equal to its fundamental period, 2 pi, divided by the angular velocity. So t is equal to 2 pi over omega, because 2 pi is the fundamental period for sine.